Guys, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this particular discussion, I'm going to look at the concept of a translation partition function. And of course, in this particular discussion, I'm going to consider some special cases of gases, and that's basically the concept of a monoatomic ideal gas. And of course, I'm going to look at some of the concepts that we have looked at, especially under the concept of quantum mechanics, or rather the description of simple quantum mechanics of systems, especially of a particle in a box. In this case, this is going to assist us in trying to describe the translation partition function of this monoatomic ideal gas. And this is going to be convenience for us, since this is the only form of motion that can be described for this type of gas. In this case, from the concept of quantum mechanics I mentioned, basically, I'm going to put a link in the description box. I've mentioned the concept of a particle in a box, and said that basically this is going to provide for us a ways of describing the specific aspect of motion of particles, especially the statistical mechanics of subatomic particles, which can be described using this aspect or various aspects of quantum mechanics. Now, in this case, we're going to consider the quantum mechanics of an atom. And of course, we have decided that from the Max Born interpretation of the wave function, Max Born argued that this basically is going to represent what we refer to as the probability of finding a particle in a box, and of course, or a particle in a given point in space. And of course, this is going to provide for us a clue of trying to represent this particular concept of translation partition function of this monoatomic gas. Now, if we may have a small reminder to say that basically for us to describe a particle in a box, we are going to assume that these specific walls are impenetrable, and of course there are going to be infinite walls given as such, and the dimension for this specific wall are going to be ranging from the value of x equivalent to 0 to x equivalent to L, and the potential inside this specific, of course, one dimension infinite wall is going to be given as 0, and this particular section is going to constitute the restricted area, which is going to be having an infinite potential. And in this case, we had used Schrodinger's equation in trying to find the specific way of trying to represent the energy of this particular, of course, particle in a box. And this is the particle translating within this specific boundaries, which we had given some, of course, conditions, of course, in trying to describe the allowed energy. Now, in this case, the Schrodinger's equation gave us a specific solution, which we had described in terms of UV given in terms of the product of the nx squared plus ny squared plus nz squared. And this was with the product of Planck's constant given as such, all over the square, all over the product of ml 8 ml squared given as such. This L represented the dimension of this specific box, and then we're going to see infinite wall, and then we're going to see that the x, y, and z components are going to represent the equal energy levels of these specific quantum numbers for n given as such, and of course this is going to be a square of this. And of course, this particularly gave us the solution for Schrodinger's equation for a particle which I've mentioned. And we're going to consider this specific aspect, and it's going to give us a relationship of describing this specific monoatomic gas as a particle which is translating within that specific box. Now, in considering this particle in a box idea, we can be able to see from the specific solution that we had described, also using the sine function given in terms of this wave function. And this one gave us the solution given as the sine of pi n x all over L given as such. And in this case, we have decided that basically, if we are going to consider this specific particle using the values of n, we're going to consider each of this one. Now, in this case, I'm going to consider the value of nx, and this is going to give us the solution for this particular wave function. Now, we are going to see that this potential inside this particular box is going to be equivalent to 0. And from Schrodinger's equation, of course, a version of one dimension, we had given a particular solution which is going to be given in terms of the negative h squared all over 8m or 8 pi squared m. And then we have this one using this specific part of the differential operator, considering only the x component, which of course gave us a single direction. And of course, this was multiplied with a wave function given as such. And we say that this is going to give us the solution for this specific product of the wave function at the energy. And therefore, we can solve for the energy from this specific equation and obtain a value which we had mentioned was giving us the allowed energies given in terms of U is equivalent to the values of x squared, h squared, all over 8ml squared. And we say that this is in consideration of a one-dimension box. As we can see from the differential operator, we have only taken one aspect of the Cartesian system, which is going to be x. And therefore, this is going to give us a solution for one component of x for describing the energy of this specific particle in a one-dimension box. So for the translation partition function, we're going to consider the three aspects of the degeneracies of n, or the quantum numbers of nx, ny, and nz. And therefore, this is going to be giving us a particular description for the translation partition function given in terms of those three components. And therefore, we can have a general case for representing that translation partition function for this monoatomic ideal gas in terms of Q, which is going to be the summation of the nx component, the summation of the ny component, and the summation of the nz component. And remember, from the laws of exponents of course, therefore, this is going to be having a specific implication, which we are, of course, I'm going to mention later. So this is going to be the negative value of nx squared plus ny squared plus nz squared, and this is going to be multiplied with and this, I think I can do away with this. This is going to be multiplied by the square of Planck's constant all over 8ml squared given as such. And of course, that's going to give us the total partition function. In this particular case, I said that basically this is going to represent this aspect of energy, which is basically U. Now, in our representation of the translation, or rather the partition, general representation of the partition function, we had this specific aspect of beta, which basically represented 1 over k bt, and therefore we're going to include this one as a k b bt given as such, and that's going to form a general representation for the partition function, the translation partition function, taking into consideration of these three components of the various quantum numbers for x, y, and z for this three-dimension coordinate system given as such. Now, from the laws of exponents, we can try to simplify this specific equation, which is basically going to rely on this specific relationship where if we have the sum of the exponents given as such, we can give this one as the product of the exponents of a and the exponent of b given as such. And therefore, this relationship is going to assist us evaluate this particular equation, which I've given at the top of that particular section. Now, in this case, we are going to have to evaluate this using the relationship which I've given below. And therefore, we are going to have this translation partition function given in terms of the summation of the nx component, of course, of the exponent of this specific value. So we're going to have the component of n given in terms of nx squared h squared all over 8ml, and that one given as mlkbt, and then that is going to be multiplied with the exponent of ny given as the summation of the exponent of ny given as negative ny squared h squared all over 8ml squared kbt. And this, of course, is going to still be multiplied with the summation of the exponent, or the summation of nz of the values of the exponent. I'm going to do away with this. So this is going to be the exponent of the negative value of nz squared h squared all over 8ml squared kbt. And all of this using this specific relationship, then therefore is going to form a summary of this specific representation for the component of nx and y, ny and z for these three quantum numbers. But in case we consider a particle in a box, and whereby this specific particle is going to be a cube, these three levels for energies of x, y, and z are going to be similar. So in this case, this specific representation, in case we consider that specific condition, then therefore can be represented as a single representation, whereby we're going to compress these ones and be given as a cube. So therefore we're going to have this one given in terms of the translation partition function is equivalent to one of the components, since we have said that it's going to be the same, the energies are the same, the exponent of negative nx squared h squared over 8ml squared kbt, and this is going to be given as a cube, given as such, considering the fact that those three components are going to be the same. So this is one of the ways in which we are going to consider the translation partition of a monoatomic ideal gas. And in this case, this is going to provide for us a window of trying to find other ways of finding evaluation for such a kind of models considering the monoatomic ideal gas. So catch us in our next video as we're going to look at the second aspect of the translation partition function, and that's going to form our final bit of this specific aspect of the translation partition function being represented using this specific equation. Now catch us in our next video as we're going to look at another version of this particular equation, and that's going to form our final bit of this specific discussion as I've mentioned. So that is it for now, guys. Bye, God bless you. Catch us in our next video.